Hello everyone, today I'm going to talk about how a robotic snake traverses large obstacles using vertical bending with contact force feedback. As we all know, snakes move incredibly well in complex 3D terrains by bending their elongated body in all 3 dimensions. Previous snake and snake robot studies have found that they can generate propulsion using lateral bending to push against these vertical structures on a horizontal plane. However, we know relatively little about whether they also generate propulsion from vertical body bending and whether they can utilize terrain height variations. Henry Astley's lab recently found that the snake can use vertical body bending to push against the environment to move forward. This was confirmed by measuring the reaction forces on these horizontal rods as shown here. The yellow curve shows the fore and after force, and the gray curve shows the lateral force. The impulse from the fore and after force was much larger than that from the lateral force, which shows that the snake generates propulsion in the vertical plane. They also found that the snake can do similarly in a channel with a triangular block. Initially, it uses concertina to move slowly forward, but once it reaches the triangular block, it no longer uses concertina and uses vertical bending only to move forward. We recently also found that the snakes may use vertical bending to potentially push against the complex terrain such as the robotic terrain. We use a high accuracy method to reconstruct the body to get how it contacts with the terrain. Here shows an example of the reconstructed body surfaces reprojected back to the camera views and a flattened sagittal view with reconstructed body and the terrain outline below it. Then we can count how many contact points are likely used for propulsion. For example, here, this blue contact point likely pushes against this higher block, and these 3 red points likely push against these 3 horizontal edges. We did not count the ones that are not likely generating force pointing to the forward direction, for example, these 2 red ones. Then we found that the snakes likely used lateral and vertical bending similarly to form these potentially propulsive points. This combination of lateral and vertical bending may drastically increase the number of push points available in various environments common in nature. This expanded range also allows snakes to better maintain propulsive force continuously and give them redundancy to improve stability and efficiency. But to benefit from this, we need to know how to control vertical bending for propulsion. In both recent studies, the animal seemingly just propagated the shape down the body, and this feedforward controller may be promising in generating propulsion like this. In fact, they confirmed this using a snake robot using the feedforward controller to successfully traverse a horizontal ladder. Here, we further hypothesize that this feedforward propagation in the vertical plane is propulsive if the shape matches obstacle geometry, but it will struggle in novel terrain of different shapes. And in such a novel condition, feedback may be the one that helps snake adjust their body bending to adapt to these changes. For example, a corn snake can adjust its bending pattern based on the available contact points in the surrounding environment when traversing a peg array on a horizontal plane. Similarly, a force feedback-based model has replicated the traversal of an array of pegs. And we know that snakes may use mechanical receptors such as tactile sensing for feedback control. Their skins are able to sense tactile information such as a poke like this or a constant load like this. So we further hypothesize that the contact force feedback can further improve performance by adapting to unknown perturbations and pushing against the height variations. To test this, we use a snake robot as a robot physical model because it's very hard to alternate control structures in animals. The snake robot has active pitch joints to bend vertically and also passive wheels to reduce friction. We also installed force sensing resistors between the wheels and the snake body so that it can measure the normal contact force applied to the wheel, which will compress the spring and that the force sensing resistor has a reading. We challenged the robot with different perturbations, each with 3 trials. The first type is 3 different horizontal resistance applied by hanging a weight using a string via a pulley system. We use this to test how large propulsion the robot can generate. The second is an unknown obstacle in front of the robot. And the third is an inaccurate shape to propagate down the body, which has a very poor contact. We generated this shape by first placing a wedge below the robot and let the robot remember the shape to propagate, but retreat this wedge before the propagation start. So for feedforward shape propagation, we use a fixed shape to propagate down the body. And we found that if we use a shape that matches the terrain geometry, the robot is able to traverse an obstacle as high as 11% of its body length. It's also able to generate propulsion as large as 3 times its own frictional drag. And this confirmed our first hypothesis that feedforward propagation in the vertical plane is propulsive if the shape matches obstacle geometry. However, it struggled in novel terrains of different shapes. For example, if there is an unknown obstacle in front of it, or if the initial shape was inaccurate, then it will lose contact substantially and unable to fully traverse the obstacle. And this confirmed our second hypothesis that feedforward propagation will struggle in this novel terrain of different shapes. To study whether and how force feedback helps robots, we use controllers with different types of feedback signals. The first is a feedforward shape propagation, and the second uses internal joint angles and velocities to control the joint torques, similarly as animals using proprioceptors to control their muscles. This one bends the head downward with a constant torque, while let the other joints follow their anterior ones to propagate the shape downward the body. We also tried 3 controllers using external force as feedback, similarly as animals using mechanoreceptors to control their motion. The first controller adjusts the pitch angle of the head to maintain a constant contact force on the first wheel, and the rest of the body simply propagates the shape down the body. The second one propagates the shape down the body while conforming part of the body to maintain a good contact force with the ground. So to do this, when a wheel senses a very small force, the 3 joints around it will work together to push the wheel downward for a larger contact force. We only apply this to the sections on the front side of the obstacle and on the horizontal ground, but not to the sections on the hind side of the obstacle, because we don't want to add additional resistance to the robot. The last controller is a shape propagation controller, but it also uses the local contact force information to push harder against beneficial contact. For example, this peg behind it, but not the peg in front of it. We tested each of the 5 controllers under each of the 5 types of perturbations for 3 times and compared their performances. Here are our observations. When there is a very small resistance, all the controllers help the robot to successfully traverse the large obstacle. But starting from the medium resistance, this internal force-based controller failed because it's not able to generate sufficient torque to overcome the resistance. And when challenged with a large backward resistance, vertical bending, feedforward vertical bending is still able to generate large propulsion, and the contact will maintain. But the internal force-based controller still failed because of the insufficient torque. These 2 feedforward controllers using external force sensing perform similarly as the feedforward shape propagation, but the partial conformation controller became unstable and failed. This failure is likely resulting from it's unable to predict its own states relative to the environment very accurately, for example, its own pitch angles. And we think adding more sensors such as an IMU may help it to better estimate its own states and resolve this issue. And when challenged with an unknown obstacle, the feedforward one failed because it's unable to adjust its shape and lost contact and lost propulsion. But feedback controllers can help it to adjust its shape to regain contact with the ground, and generate sufficient propulsion to traverse it. And provided with an inaccurate initial shape, both the feedback controller based on internal sensing and the first two controllers based on external force sensing helps it to regain contact and regain propulsion. But this active controller failed. It's likely because this one was designed for a robot moving on a horizontal ground and did not consider the effects of gravity. All these confirmed our third hypothesis that the contact force feedback can further improve performance by adapting to unknown perturbations and pushing against height variations. Lastly, we further compare the contact conditions and propulsion. We quantify contact by using the average lift-off height between the wheels and the ground, and the propulsion was calculated as the sum of horizontal force components applied to the obstacle. Our findings further confirm the hypothesis. First, if the shape matches obstacle geometry, shown by this very small lift-off height, feedforward propagation in the vertical plane is still propulsive and can generate this large propulsion. But when it's in a novel terrain of different shapes, it lost contact with a large lift-off height and cannot generate the sufficient propulsion. And also, force feedback controllers can help to improve the contact by reducing the lift-off height and increase the propulsion, shown by this increased propulsion compared to the feedforward one. In the future, we need to improve the controllers more. For example, how to maximize the propulsion by adjusting contact force distribution and using centralized plus decentralized control to save bandwidth for faster response speed. We also need more accurate measurement of terrain forces at more locations, and we are building a sensorizable physical model for this to study how forces are generated and can be controlled. We also hope to have the funding to build a sensorized terrain to measure the forces actually generated by the animals. Lastly, I want to thank my lab mates and the funding resources, and I'm happy to take questions.